thank you for inviting me. It's nice being among this group of people, and essentially I had kind of two things to talk about. One would be more sexy research, and this is more the sensible, safe research that people often ask me about in terms of what they should do or they shouldn't do if doing searchlight maps. And so a large part of the talk is a tutorial on what you can do in terms of training pattern classifiers within searchlights and how you should test those. But so that I don't bore anyone, how many people are comfortable with classifiers? Good, okay, so I won't bore too many people. I usually feel obligated to give a tutorial on the topic, and I find that people expect me to give a tutorial and then they will not revert certain details, so I might as well ask and do it. So, and how many of you have seen the original Searchlight paper? Okay, so the basic idea was to say you want to answer the question of where there is some sort of activation difference between two different conditions. And normally, in completely vanilla GLM, you learn data images for each of the two conditions, and you'd have tests to say that where if at a given voxel there's a difference or not. And the idea put forth by Nico Krieger-Skort in this paper was to say, what if we know that voxels are not acting in isolation, so what if instead of just testing for the difference between conditions at a voxel, we look at the neighborhood surrounding a voxel. So we trust a voxel if the voxel plus its neighbors are doing something different between the two conditions, rather than just trust a voxel by itself because they're noisy. And so what he compared in this paper were three ideas. One would be just the standard univariate T-map. The other one would be to say, if we're going to assume that the neighborhood has some meaning, then we might as well just smooth the data and hope that that gives us better scores for a voxel, because now you're taking into account what it does and what its neighbors do. And if they all do the same thing, you trust the voxel more. That's the intuition. Or he actually also looked at a multivariate statistic within a small window covering, say, a little sphere of voxels. And what he's doing here is saying, we're not averaging, we are saying, is there a difference between the beta weights for faces within this small window and those for houses in that small window? And you also take the covariance between those voxels into account. So the way this differs from smoothing is to say, maybe one voxel is going to be positive for houses and negative for faces, and the neighbor next to it is going to be the opposite. If you smooth them, they pretty much cancel out. In this case, it's saying, well, if my covariance matrix tells me that these guys move in opposite directions, I can integrate that information.
That's covariance over what?
Sorry?
Covariance over what?
I think it was what we estimated when fitting a GLM to get the betas, as far as I could tell from the methods section of the paper. But I don't fully recall the details because it was a while back.
Over the time course.
Yes, because it begins by fitting a GLM and getting betas, and then he uses this statistic on the beta image. And so what's I'm trying? Sorry, the gizmo to change the slides manually doesn't work. It probably won't work with Linux. Am I blocking the screen for people? Maybe. Yeah.
Careful.
Okay. Good. Well, not so good, but is it still visible?
Yeah, let's try to.
Just talk louder, we'll see it.
Oh, and I should talk louder for Clark. Thank you.
How's that?
Good. Thank you very much. Yeah, so the comparison here was essentially saying that if you take the original unsmoothed data and look at the T-maps, you can see a few things. If you smooth it, you'll actually increase what you can detect. So essentially, yes, smoothing will get rid of some of the noise, and the voxels that remain are voxels you can trust more. And the searchlight will actually improve it further relative to the smooth data, which indicates that you aren't just getting noise reduction by smoothing, you are getting something from considering that the voxels vary together in a certain way. The rest of the talk is not so much about, and he used permutation test p-values to test this, and I'll get into that later. So I'm introducing this because, on one hand, it's historically relevant, but also because the idea of looking at small windows kind of became very pervasive. And in particular, people combined it with using pattern classifiers, which I'll also talk more about at length in a couple of minutes. And the idea there is to say, well, you can train a classifier, which is going to be the proverbial black box, on to learn in each little window to make a prediction, such as, okay, which condition is the subject in? Is the subject looking at houses or faces? Or, as in that John Dylan Haynes paper, what's the guess? What's the thing that the subject is going to guess, or what operation are you going to do? So essentially, you might be learning to decode things that you don't really have regressors for, a priori. And so this gets used really, really often. There's tens of sites for this, and essentially for two purposes. So that one of trying to say, where can I make the decoding, and actually have a very precise location for where the information about what we want to decode is. And also as a step for selecting informative voxels to feed to a whole brain pattern classifier. We have some results on how to do this, but they're not in this talk, otherwise this would just get completely out of bounds. But if you care about selecting voxels, you can ask me later, and I'll be happy to tell you all that I know. And before I launch into more details, I just want you to have in mind what a searchlight accuracy map would look like. So that's going to be at every voxel has a value that's essentially its prediction score, using that voxel and the searchlight around it. So just for this talk, it's just the voxel and its immediate neighbors in 3 dimensions. This can in turn be converted to a map of p-values, and in this case, which is a map with a binary classification task, you'll have the accuracy in each voxel of the classifier in that neighborhood. And also, in the plots that I'll show you, I also have the number of voxels that in this slice actually passed a statistical test and are deemed significant in terms of, yes, the classifier is finding some information in that location. So whenever I talk about accuracy maps in this talk, keep this in mind, and then later we'll see a lot of them. But in the process, I'll allude to this over and over, and this is the image I would want you to keep in mind. Any questions so far? So forgot to say that you should ask questions, because a lot of this is prescriptive or tutorial, so you might as well ask. So for the rest of the talk I'll begin by telling you more about what's on the black box, especially because some of the people don't know so much about classifiers. And then I'll get into the nitty-gritty of why the choice of classifier actually matters somewhat, or in what circumstances it will not matter, and where that ties into how the choice limits what you might be able to find or not be able to find, and how you actually should try different classifiers to look for different things. And most papers just use typically 1, maybe 2 if you're lucky, and so they could be missing quite a few things, but more about that in due course. The data sets I'll be using, there's 2 of them. For this part of the talk, let's focus on this one. It's one where the subjects were just reading concrete nouns, names of either types of tools or kinds of buildings. And the typical trial will be subject sees a word, has to think about it and visualize it, or think about how they use it if it's an object for 3 seconds, and then you have 8 seconds of blank where they're supposed to empty their minds. It's not the best task in the world. I've done this. It's a pain in the neck, but you can actually still decode from this sort of data. And every trial gives rise to, say, one average image at the peak of where the signal is in the trial. And that's really what the classifiers get to see. And we'll also get into more detail about that. So you'll just have a lot of one image per trial, and you know what happened in that trial. The subject saw a tool, or the subject saw about a building. And a bit more terminology here. So I'm calling this average trial image an example, and this is the typical machine learning terminology. Every example comes with an associated label. It can have more than one if there are more things going on in the experiment. For instance, if you wanted to predict which specific exemplar it was, it could have a label which would be the category and another label which would be exemplar. And in this case, I'm thinking of just taking all these values across the whole brain and stringing them into a long vector. which will be an example covering the whole brain. And so every voxel, again in machine learning parlance, is called a feature. So this is normally what I would talk about in a talk about classifiers. In this case, I'm be talking about searchlight examples, i.e. just a portion of this vector that corresponds to one of these little windows. Is it all clear so far? And so there's two major classes of types of classifier that I wanted to describe, and the general principle, they all either class has one specific organizing principle. In the case of the Gaussian classifiers I'm describing here, what the classifier tries to do is to say for a single voxel, say, well, I have so many values of this voxel while the subject is thinking about tools, so condition A, and so many values where they're thinking about buildings. And we're going to say, well, what a voxel does is have one mean value in one condition, another mean value in another one, and then there's noise on top, and the noise is Gaussian. So this is the exact counterpart of doing a t-test. And you can do this on a normal image, you can do it on smooth data. I'm doing this just for comparison with the searchlights that I talked about earlier. And if you want to go below, so this doesn't really use a searchlight. This is the classifier you could train on every voxel by itself. But it's usually a good baseline to have to see if training on a searchlight actually improves things. If you actually want to model what's going on in a searchlight, now you're saying, instead of assuming that every voxel is a mean and some Gaussian noise on top, you are saying voxels in a searchlight covary in some way. And you can estimate their mean for tools and for buildings, and then you can also estimate what that covariance matrix would be. And I'll use all of these, but naive Bayes, which you'll probably hear, well, you'll hear more about this later, is the simplest kind, where you say, I'm considering all the voxels, what all the voxels are doing, but I'm not really considering their covariance. So if you're learning to make a prediction with a model like this, you're saying you look at what a voxel does, what all its neighbors do, and you aggregate this somehow. You might have come across Fisher's linear discriminant analysis, and this is just saying, assume that there is a covariance structure for all the voxels, grab that, and then you can turn that knowledge, that model of the voxel's activation into an optimal decision, assuming that that model is true. Shrinkage LDA is something, it's pretty much the same classifier with one extra, which says you don't really estimate a full covariance matrix because you rarely have enough data to do so. What you do is estimate a diagonal covariance matrix as a naive Bayes, and if there's support in the data for considering more voxels or more interactions between voxels, then you add those two. And quadratic discriminant analysis is same thing as linear discriminant analysis, but you assume different covariance matrices for each class. And in this case, I'm doing this again with the shrinkage estimator, which is what this type of estimator of the covariance matrix is called. I'm sorry, this is a lot of detail to cram into one slide, but that pretty much had to. Any questions here?
So for the shrinkage QDA, that looks like a more full covariance matrix. It looks more like the Fisher's LDA. Is that?
This is because I was generating these things at random in MATLAB.
Okay.
And at this point, I wasn't thinking too clearly. I should have made them more sparse. Thank you for noticing. So the operating principle in these is something, these are all what we call generative models. So essentially is you assume that you can model what all the voxels are doing, and then you use that to make a decision as to which class the image might have come from. The other type of classifier is, and I'll use support vector machines as one example of this, is what's called a discriminative classifier. So instead of trying to model the joint activity of a group of voxels within a searchlight, you directly say, I want to learn a function that looks at a pattern of activity within that small window and makes a prediction of whether it's tools or it's buildings that the subject is looking at. In the case of a linear SVM, there's a certain criterion for deciding what weights to use, but all it means is that you're going to take the values the voxels take within that window, multiply them by weights, to take that linear combination, and depending if it's positive, you predict one thing, if it's negative, you predict something else.
How do you select the weights?
So the criterion is you're going to select them to maximize the margin between the two classes, which is probably more detailed than I should get into here. But I can tell you more about it later. There's many possible criteria, so this is just one type of discriminative classifier that I could use, but it happens to be one that we can train relatively fast. And again, this is more to be exhaustive, so you could also train, there's more classifiers you could use, and let me just tell you about those in a second. There's also nonlinear support vector machines, which are, it's a similar idea. You learn to just take a weighted combination of things to make a decision, but instead of doing it on the original voxels, you do it on functions of those voxels. To make this more concrete, so I was showing you the linear SVM earlier, so you just combine voxel 1 and voxel 2, assuming a searchlight has only 2 voxels, and you make a prediction. This is a quadratic SVM is a bit like doing a linear regression with an interaction term. So you consider what the voxels are doing, but also what their interaction is doing. And then you train a linear discriminant on that new feature space derived from the original one. Does this make sense? Okay. In the case of SVMs, and again, more detail than I should get into here, you don't explicitly produce this like this interaction term as you would in a regression. It's implicitly present in a mathematical problem by the use of something called a kernel function. Again, I'm not going to get into too much more detail. It's just that you can have these arbitrarily complex functions that produce complicated feature spaces that allow you to learn complicated functions mapping the voxels to the prediction. And all the ones I'm including here are here just because people have used them in one paper or another, and my interest was in actually having a fairly exhaustive comparison. And so and I was talking about learning complicated models. You could also ask me if you've seen classifiers, why can't we learn something more complicated like a neural network, where instead of saying you learn a linear discriminant on these new feature space, you actually learn functions of the original voxels, which is what would happen when you train a neural network. The reason you don't do this is that these are very costly to train, and everything you do in one searchlight you'll have to do in 10,000, so it will take way too much time. And there's also the danger of overfitting. Again, this is a technical term, but in practice all it means is you can learn an arbitrarily complex model within a data set that will make the prediction, that will predict perfectly within the training set. But what happens is if it gets beyond a certain level of complexity, your error on a test set, on say a new data set you look at, will actually increase. So it goes back to what Clark was talking about earlier, is you want to find a model that's complex enough to capture the relationship between what the voxels do and the thing you want to predict. You don't want it to be more complex than it should, otherwise it starts fitting all these idiosyncrasies in your training data. So I usually hesitate in giving a complete classifier introduction that early in a talk, but in order to actually talk about what I really want to talk about, which is this, I really had to get all of that out of the way. So we have multiple classifiers mainly because they've all been used at some point. And the crucial thing, and this is what Bill was asking about yesterday, is because they all make different assumptions, they are going to postulate different relationships between the voxels and the thing that you want to predict. And you don't really know a priori which assumption is going to hold or which relationship is going to be present. So you don't really have a strong reason for preferring one or another. And in fact, in the literature, people tend to pick SVMs because they're popular and they've heard of them. But there's no principled reason for doing so. So the question that I'm really interested in is, does it really make any difference to pick one or another? And do you actually get similar results? Do you get wildly different things? Because I review papers where people claim, I found this here and there and there, and what if they had used a different classifier? What would they have found? And that's kind of the question that I'm concerned with. In case you were wondering about this was Procruste's bed, but mostly because people have this way of trying to make the data fit the classifier that they pick rather than the reverse. And my hope was also to try and understand what the classifiers could learn in real data so that I could tell people, well, if you are hypothesizing this sort of relationship, then maybe that classifier is a better choice than another one. The other thing that I wanted to discuss just before getting into the meat of this is, in this data set, the examples come in groups, which are just, there's 14 different types of tools or buildings, and they all appear once before repeating. So you have several different groups and in an entire data set. And the reason I'm saying this is the way we test predictions is by training the classifier, say, in the data from one searchlight and its labels, and say 1/2 of the data, the odd groups. You learn this classifier and then you apply it to some test data it hasn't seen before. And you make a prediction of what the labels for these examples should be. And you have the true labels, and at that point you can compare the true labels with the labels that you predicted, and you have an idea of how well that classifier can do. And to make this a bit more concrete, so for any classifier you're going to have a sequence of predicted labels in your test examples, and you have the true ones, and you can compute how many you got correct. And essentially what people want to show is that the number you got correct is higher than you'd expect to see if the classifier had learned nothing, you'd expect it to predict no better than someone tossing a coin in this case. And that's usually what people have in mind when they want to say, no, my classifier learned something because it can predict better than a random model. And so the random model in this case really can be, with two classes, can be viewed as tossing a coin. So if you look at x as the number correct, under that null model that the classifier is predicting entirely a chance, the number correct would be, has a binomial distribution, and the p-value for that is the one that you'd expect under that binomial. And the thing to keep in mind, and it's really important here, is that if you only had, say, 10 test examples, this is the shape that binomial distribution would have. So it's not entirely unlikely that you'd get all of them right or none of them right, say. But as you increase the number of test examples, that thing gets narrower and narrower and narrower, and eventually it will get to be entirely around 0.5. And so the reason I put this on the board, usually put this on a slide, is because 100 examples is typically above what most people have. So this is to say, if you're training a single classifier on the entire brain, you'd still be wrestling with this. Now imagine that you train 10,000 classifiers and you only have 50 examples. Quite a few of them, by chance, will, even if you learned nothing, are going to predict the labels reasonably well, just because of numbers. Is this clear? Good. And the other thing to keep in mind is that the accuracy we get on a test set is an estimate. So it's saying we have a certain number of test examples, we get this number correct, it could have been more, it could have been less. The thing we're really interested in is how accurate would that classifier be if you had an infinite number of examples, but you don't. If you have an infinite number, you would get to be around 0.5 if you were a chance. And because you don't, usually if you really care just about the actual accuracy number, you could get a confidence interval on that takes that size into account. But the other thing that you must do in this case is, if you train those 10,000, you will need to correct for multiple comparisons. I'm going to talk about cross-validation. Have you encountered the concept? So essentially, in this case, it would be to say you want to use as much of the data as you have to train a classifier, and then test on a little bit that's left out. And then, so it could be the 6th group, and you could do it for groups 1 through 5, training on the rest in turn. So the idea is that you get to use every single bit of data in your data set as a test example once, while you use the rest of the things for training. So whenever I talk about cross-validation, that's the procedure that I mean. And does that make sense? Okay. All right. So that was all the formal stuff that I had to get through. So the rest is mostly graphs and things in actual real data. And thank you for bearing with me this far. So you've seen this data set. The thing I didn't really get into details was how many examples we had. So 48 of each kind. And you typically have in the brains from this data set 10,000 to 20,000 features. The second data set is the data set that was talked about earlier. So it's from that Jim Haxby's 2001 science paper, where subjects are seeing photographs that belong to one of 8 categories. And the examples in this case are, you have a block of images of the same category, you average the images within that block, you get a single image which as an example for each block, and its label is the category of the thing that was being shown. So the classifiers that I'll use here for comparison are the ones that I already described to you. So the ones just not actual searchlights within one voxel, and then all the other kinds. The way a map is created is you are training and testing a classifier with cross-validation within each searchlight, and then you can transform that into a p-value using the null model that I just described to you. So you get an accuracy value, you see how likely it will be under that null hypothesis of the coin tossing. And then you can threshold that using, I use false discovery rate with the most stringent threshold and with that rate. And you'll get a certain number of you get the accuracy map like the one I showed you earlier, and a certain number of significant voxels. This is more if you care about doing many comparisons of classifiers. All that it says is I can do this for many classifiers. I can find which voxels were significant in any of them, and then compare across those voxels what accuracy each classifier gets on each one of them, and turn that into saying a certain classifier is better than another classifier across everything that's significant on any map. The details don't matter so much, just to say that this is, I can do this, and if the difference in accuracy is not large enough, it will not be deemed statistically significant. And if you care about doing that sort of comparisons, do ask me, because I have code for running these tests. But what I really want to show you is what it actually looks like. So in this plot, positive means that one classifier does better than another by a certain amount of accuracy. So in this case, it's a 2-class problem. So 15% is actually a really large chunk of the score. Anything that's gray is not statistically significant in terms of comparisons. And so what this shows is that naive Bayes actually does better than the other classifiers, or at least certainly no worse looking at these. But a number of other classifiers, like the SVM with an RBF kernel, also do fairly well. So there was nothing really compelling other than showing that these were a little bit better. There's a few more down here which are SVMs where you actually cross-validate the parameter settings. But again, if you do this sort of thing, come ask me about that. Otherwise, I will not belabor the point. And we found that for certain types of data sets, it pays to cross-validate the parameters of an SVM if you use that. With the 8 classes, it's actually the things actually look a bit more interesting in that LDA with shrinkage actually does better than naive Bayes. And all this means is that now that you have 8 classes, when you have 2 classes, the voxels can't really be doing that many things. So maybe they are positive for one class and they're negative for the other, or vice versa. So it probably doesn't pay very well to learn any kind of local structure. And that's why naive Bayes, which learned that diagonal covariance matrix, did really well. Here, though, you can already imagine that voxels in a certain neighborhood might have interesting interactions with each other. Because, yes?
I'm just wondering, 8 classes are your external criteria from the definition of your experiment.
Yes.
So how do you actually know whether you have 8 classes in the data?
Ah.
Could be that you have just 4 categories.
That's an excellent question, and the answer to that will come in a few slides.
Okay.
Yeah, in this case, we don't really know. So all I'm doing is saying train the classifiers on every searchlight, compare across all the voxels that are deemed significant on any map. Does it do better? But it's unclear that whether the better from this diagram you can tell whether the better is distinguishing 8 or distinguishing 4 or distinguishing 2. Just that it's a little bit better and it seems to find some local structure. And so you get a bit more accuracy out of modeling local structure. And this is sort of a theme that appears in many searchlight papers, is the paper will say, we are doing this because we want to get at the fine structure of activation. And rarely does a paper tell you what exactly did they find in terms of sort of a local code of some voxels doing one thing while others do something else, or a nonlinear function connecting two voxels that corresponds to encoding of a certain bit of semantic information. So rarely do people do that. And part of the goal of doing this was to say, if you're looking at a classifier that can do it, does it actually learn something given that ability? Or does it do no better than a classifier that just aggregates information locally in the most simple way? Now, so that was just to compare the different classifiers and to give you a rationale for my picking the ones that I'm picking at this point. So in this case, I'm just comparing the one where you train a single Gaussian classifier per voxel, the naive base, the LDA with shrinkage, so you're learning a covariance matrix, and also one of the linear SVMs. What you have on the side is also the number of voxels overall that were deemed significant. So the number varies somewhat, but the thing that's really striking when I looked at these maps was, even though the number of voxels deemed significant changes from map to map, the maps look really, really similar. And if you want to really quantify how similar they look, you can look at two things. One is just how correlated they are across space. And the answer is, except for the first one, they're very highly correlated. And then how many of the significant voxels appear in two maps versus appearing in only one of them. So i.e., in this case, I can look at map number 2 and map number 4 and see that out of all the voxels that are deemed significant in either map and the intersection, that fraction is around 50%. So even though they are very highly correlated, there are still voxels that one of them will deem significant and the other one won't, and vice versa. So if you're only training one, and this was somehow important to you, you might not ever discover that there were other voxels that would pass the threshold. Or this tells you that there's a lot of things that are just on the verge of being significant or just a little bit above, and they are in one classifier and they're not in the other, because the accuracies are estimates and they fluctuate around the true accuracy. And that's why I was belaboring that point earlier. So this is not such a precise measure that once you find it, it really is there. It might be just around the threshold. Any questions about these plots? Okay. Now, to answer the question that you had, when you have 8 classes and you actually plot the accuracy of any class of the classifiers that did best at doing this 8-way discrimination, so which of the 8 possible things it is, the accuracies you get are on the low side. So you might see around 25% at best, maybe 20%. The thing is, when your chance level is 1/8, so 12.5%, you don't have to do much better than that to be deemed significant. So whenever I see a paper that says we get this extraordinarily above chance accuracy, the question is, but what does that mean? So what does it mean for a classifier to do 20%? Does it mean that it's does 20% of the examples in every one of the 8 conditions? Does it mean that it can do faces and houses really well, and then it doesn't do anything else at all? And from these plots, which is what you would see in many papers, it's not clear. Nevertheless, the number of voxels that are significant in these plots is just huge. I mean, you might have 3,000 voxels that are significant strewn all over temporal cortex, which was the original point of that Haxby paper, was that, yes, you had information all over temporal cortex, and this is showing you precisely that. But it doesn't tell you much more than that. And again, the maps are really highly correlated, and in this case, they actually share more of the voxels, maybe because there's just a huge chain of voxels, and these things overlap. Any questions about this or multi-way?
Do I correctly understand that these maps correspond, say, to a slice of an MRI?
Oh, I'm very sorry. That's exactly what they are. Several
Yeah.
slices in this case.
So most of these voxels are actually not in the cortex.
Well, you have to look at the way the slices are taken, which I don't remember exactly in this case.
Yeah, but usually I would expect that there is some kind of band, some sheet on the outside. Well, I'm just wondering how to interpret those maps.
Yeah, well, I can't do it over, I will not do it over structural images, and it's been a while since I looked at those, but I will do more in the way of interpreting what's going on.
Okay.
So what I was also concerned with was trying to say, then if there is some sort of interesting structure happening locally, and going back to dataset number 1, i.e. in places where learning a covariance matrix actually gives you more accuracy than just aggregating over voxels in a searchlight, you can ask what is being learned. You can say, for every searchlight, what's the covariance matrix that LDA with shrinkage is learning? And thus far, I could find some voxels will just have this kind of little mini mobs of voxels acting in concert, or I've seen other voxels that look more like this. Some things will be anti-correlated with other things. And there's a few others where it's hard to say what is going on without looking at the mean activity of all the voxels in either condition, which I unfortunately didn't record for this study. This is more to show you, this is how you could use multiple maps to get at the local structure. You could say, I train a map that learns a covariance structure locally. I train a map that doesn't. And I look for the places where having more structure performs better than having less structure. And then you can go and look at that, rather than just report and say, my map found accuracy in this place or that place or that place. And for some people, there might be a compelling reason to test whether voxels are doing some interesting thing together in a neighborhood. And this is how you go and try to test that sort of thing. Any questions about this? Okay. So what I really wanted you to take from this was that if you really care about mapping information, yes, it pays off to use searchlights. There's no clear advantage in using a nonlinear classifier, at least in the data sets we looked at. So not just these two, we have several other multi-way classifiers and a few other two-class problems too. And even though the maps are similar, you will find different significant things. I mean, the number that's significant differs, and the precise locations where they are also differ. So if you really are concerned about mapping, it would likely be preferable that you train several of these and even take their intersection, rather than just train one and report on what you found with just a single one. And there's no reason for you not to do this and just threshold them a bit more aggressively, because as you saw, there's still a lot of voxels that might pass the threshold, at least if tested in that way. So the other thing to keep in mind is that you should be willing to go and look at what the local structure is. So I showed you some local covariance matrices, but you could also, if you're training a local linear SVM, you could go and look for the weight vectors that are learned in a certain place. And in a two-class problem, it might be some voxels are up and they have a positive weight towards, they're positive for tools, and they will drive the linear discriminant to predict positive. Others will will go positive for buildings, and they would have a negative weight to again drive the discriminant towards tools, or towards buildings, depending on what it is. So the idea is there's no reason why you shouldn't go and look at what's happening in the neighborhood of the places that have the information. The other thing to keep in mind is that you can, as I was telling you earlier, subtract some maps from others and find locations where one map performs better. And as you train maps that make different assumptions about what's there, you can use that to do a test for where there's complexity, rather than looking at every voxel in the brain or not looking at all. So it's a bit like what Clark was saying about the bears. You want to find what's right or not. The other thing to also keep in mind is that if a classifier that's complex does not perform better than a classifier that's simple, that doesn't mean that there's no complex information there. It just means that maybe you don't have enough data. If it performs worse, you know that it's overfitting. If it performs better, you know that it found structure that the simpler classifiers couldn't. The other thing that I was interested in was whether the permutation, testing this with permutation tests rather than an analytic test would make any difference in terms of what you would find significant. So we already talked about how to do this analytically. The permutation test approach is, the intuition is really simple. You're saying there's no difference between my two classes, between tools and buildings, in any of the searchlights. And if that is the case, the labeling of examples as being tools or buildings is completely arbitrary. So you should be able to permute them, to permute those labels up to exchangeability, and some people will be take this a bit seriously, so I don't want to offend anyone. If you can test for exchangeability, by all means do. You can ask me about how you can test for that in examples. And you essentially use that permutation to estimate the distribution of the accuracy under the null hypothesis. So you say, permute all my labels, create an accuracy map. Permute the labels again, create an accuracy map. And then you see, you do this 1,000 times, 10,000 times. And then you say, for every voxel, how many of these maps under permuted labels does the accuracy that I got with the true label beat that? Does the logic of this make sense? And the p-value is intuitively just a fraction of repetitions where you actually manage to do that. So what's qualitatively different here is to say this is a null hypothesis about data rather than about the classifier. We are saying there's no difference between the two conditions in the data, rather than saying the classifier learned nothing and is performing a chance. And this is easier to explain to people than the analytic test that I described, because you saw how many slides that took, and this is kind of intuitive and simple to explain, and useful in general if you don't have an analytic test. But the cons is, in this case, we have a cheap analytic test. This is expensive if not implemented in an efficient way. It's kind of optimistic if done naively, because maybe you take examples from multiple runs when you permute the labels, and there's differences between the runs that make them make the scores worse than they would otherwise be. So it would be kind of so it would be pessimistic. And the thing that's key is this. Essentially, the lowest p-value you get is 1 over the number of permutations that you do, because the true labeling is one of the possible permutations. So given that you're doing tens of thousands of tests, you'd need really low p-values in order for them to survive thresholding with false discovery rate. And this is the reason why this is not done as often as, say, doing an analytic test. But just for us to see what this looks like, and I'll have to speed up here to tell you about the last bit because I'm almost out of time, we actually run 100 through 100,000 permutations for that 2-class data set. We have code that does 1 map per second, and even that takes a couple of days to run. And what I'm plotting here is just the log of the p-values. So in the x-axis is the analytic one. So these are the smallest p-values, the largest ones. And on the y-axis is the permutation p-value. So if they matched exactly, they would lie on the diagonal. They don't. They're always a little bit worse and higher than the p-values that are obtained analytically. And these lines are what the false discovery rate threshold would be given the distribution of p-values. For the analytic ones, the threshold would be around here. For these, it doesn't even show. It only starts showing when you've done this many permutations. And it would take about 100,000 for this scatter plot to start getting closer to that line and actually be below threshold. So if you're doing the permutation tests, this will get you. So unless you have a very compelling reason for doing so, or there's no analytic tests, in this case it would be counterproductive to do it. You'd only want to do it, and if the test examples are independent, the results should be the same under an infinite number of permutations. I'm going to skip that and just tell you about this is to answer the rest of your question about the multiple classes. So I was telling you that chance level will deem many voxels significant. And so the accuracy in a multi-class setting, as I was saying earlier, could be many things. So it could be that you do poorly across many categories, or you can do really badly in some and really well in others. So and the way to conceive of this is thinking of a confusion matrix where you just plot, for examples, in each of 8 classes, how often do I label it correctly? That's the diagonal. And I label it as everything else other than itself. So labeling perfectly would be the graph with a diagonal. As you make mistakes, you essentially are sending votes to the others. Does this make sense? So what you can do to get around this is, we would like to look at those covariance matrices, but there's 10,000, so those confusion matrices, but there's 10,000 of them in the brain. So instead of doing that, you can go directly and ask, for every pair of classes that you have, can a voxel, a searchlight, distinguish between them? So the first line in this matrix is the face versus house distinction. The second one is face versus cats, and all the way through the 28 pairs of classes that you have. And for every pair, you can ask the question, does a searchlight make this distinction? If it does, is it significant? And so you end up with this large binary matrix of pairwise distinctions that every voxel can make. And in the end, you can count for every voxel how many distinctions does it do. I'm almost at the end. And what you get is a count map that says some voxels actually get their accuracy from distinguishing many pairs of categories. So they have one type of confusion matrix. Others will only distinguish a few and distinguish those really, really well. And overall, the accuracies are roughly the same. So this is quite a bit more informative than just saying that the voxels are significant, but you rarely see something like this. So this is just to give you another idea of what you can do in a situation where you have multiple classes. You can want to go further, which is to ask exactly what the voxels are doing. And to get at that, you can see that across pairs, every voxel has a little binary profile of pairs it distinguishes, pairs it does not. And so there's 28 pairs, so there's 2 to the 28th possible binary vectors you could have. If I were to ask you, how many do you think you see in the brain out of those 2 to the 28? What would your guess be? There's only a few hundred. So essentially, what this is saying is, even though you have all those pairs of distinctions, there's only a few distinctions that are actually being made. There's only a few different informative populations present. And you can then go and see which ones appear more often throughout and plot them. Again, every one of those binary profiles is a bit like a binary confusion matrix. You either make the distinction or not. And in this case, class 8 is scrambled objects, and you can see there's populations distinguishing its scrambled objects from pretty much everything else, or faces versus all else, or houses versus all else. And in this data set, we knew these things were there and they had been commented on literature before. So, but what I wanted to give you is this idea for what you can do if you want to use searchlights in a multiple class situation. This is pretty much what I was talking about. And so this is what I would like you to take home. So that the fact that you don't see accuracy with one map doesn't mean that it's not there. It means that maybe you're just not using the right classifier. also, if you know what kind of relationships between voxels you want to learn, you should try to pick the classifier to match that, rather than just throw whatever the flavor of the day classifier is, which may or may not be able to find it. And if you try many maps, please report all of them with the correction. I mean, it's not like these things get destroyed. I showed you how many comparisons I've made between, say, 10 classifiers with themselves, and even there you could still see a lot of things that are significant. And we've talked about most of these issues in other talks or throughout this one. So the other thing I wanted to just leave you with is, and if you want to use these things, you don't have to implement this code. All the things that I've showed you can be done with the toolbox that we are writing, and we will release in December when we submit a paper about this. So if you're interested in that, feel free to email me. If you have questions about running searchlight maps, same thing, and I'm more than happy to answer those. And thank you very much.
I'm having trouble bridging between the physiological and anatomical side and the statistical things, which I'm much less knowledgeable about. And I wondered if you could make some comments about what does it mean for different analyzers to give you the same answer for very, very different kernels, very, very different analyzing techniques. Can you bridge that to the anatomy for me? Do you see my question?
Yeah.
What front you use it like? Just go up there next to that, so we can see you.
Okay. Well, there's two answers to that. One is I don't know enough about the anatomy to say anything.
But you do know a lot about distribution. And
Well, I mean, and I'll qualify that answer. So I've seen, say, data from cat visual cortex where you can actually see at the level of cortical columns, and you can see some of the interaction. So we don't have that here. So I'm really only interested in any kind of regularity that you can pick up on, even though it might be hard to interpret from an anatomical or physiological standpoint. As in terms of the several different models giving the same answer, let's say it's the nonlinear radial basis functional kernel, for instance. That will have the linear kernel as a kind of special case. So it's not a coincidence that I picked both of those. So if they do equally well, you know that the RBF is not learning anything beyond what would be on the linear. Whereas the quadratic kernel is actually different, and that one fails miserably for reasons I don't understand.
are the voxels in these that are used in the different analyses scattered all over the brain, or are they typically close together?
Well, for these, they are close together by design, and that's purposeful. If you're looking at picking voxels from all over the brain, they can be scattered all over the place. And people are uncomfortable by that, especially because if you also, let's say, you split the data. You pick voxels from one half, you get predictability. You pick voxels from the other half, there might be 10% overlap between the two halves. And this doesn't mean that there's nothing there. It means that there's redundancy in the information. It also doesn't tell you that whether there are different kinds of information or not. That you can get at by doing either searchlights or by looking at patterns of errors of classifiers based on the different things you're looking at. So if the classifiers look at the same data but at different parts of the brain, and they make different mistakes, but you are using the same kind of classifier, it learns something different. And again, you can go at it from using a whole brain classifier, or you can try to come at the problem bottom up and try to say, what are the different kinds of information in different places? We have some reason to believe that neighborhoods are meaningful to a degree, and voxels are kind of an arbitrary way of dividing the brain anyway. So it makes sense to start bottom up, at least in my opinion. Does that answer your question?
Not entirely, but I understand what you're saying. I guess what I'm looking for is evidence to support my speculation that things are more distributed than we generally acknowledge. And
Well,
I just don't have a sense for how far the alternative voxels and the two analysis techniques are from each other? Could they be the frontal one and the occipital lobes, for example?
They could.
Mhm.
And especially when you go towards multi-class, that's when you start seeing, because if it's just two classes, you can probably make sense of what the voxels are and say there's a good reason why voxels will be doing something different in this condition, in this part of the brain, in that part, in that part. Once you're talking multi-class, it really is hard to say why the information will come from a certain place or from another one. And again, that's what drove me to think more about searchlights.
Thank you.
You're welcome.